Okay, so I think this is the right number. This is 3. If it's not, I probably made a mistake. So this is illustrating example. We'll study the so-called orthogonal polynomial example. Let us focus only on the example that relate to the Gaussian unitary example. We are interested in the following probability measure. This is a normalized constant times xi it's not big enough. Square n I j. We see that this is a probability measure on Rn. Probability measure on Rn. But how to relate it to the point process on R? You see, we can see that here, the function, the density is permutation invariant. We can permutate the coordinates. So, of course, this probability is permutation invariant. So, we can look at this probability as a probability on Rn modulo permutation of coordinates. So this gives in fact a probability on the subset of R with exactly n points. Is clear? So this is, we identify these as subsets of R with cardinality with n points. Okay. Now we can see that here it is just the determinant of the Vandermonde determinant. That is why at the end of the day this probability will be can be described by certain determinant. And here, the spectrum, so the eigenvalues of this previous Gaussian unitary random matches is in the probability is described by this probability. Let us admit this and let us compute this to relate this probability to Hermite polynomial. So this probability, we have a von Neumann determinant. The determinant, the square of the determinant, this is 1 x1 to the power n minus 1, x2 to the power n minus 1. We do the same thing, but we will write it like this. So this is this part. This should be clear. And now we will do here column operation, and here the same row operation. We can replace these monomials by the polynomial of the same degree, and here probably by changing certain constant. So this term will of course up to some constant. This is p here the x1, p1, x1, pn minus 1, x1, p0, xn, p0. And we do the same thing here by transpose x1, pn minus 1, x1. Well, this identity holds, of course, for any polynomials with the degree Pn, Pk is the degree k polynomial. But why we are interested in such a formula? Because later it will be convenient to calculate things, and we will take in particular this P. We can take, of course, in particular this Pi, the i's orthonormal polynomial, orthonormal polynomial with respect to the weight.
Change marker, please. Change your marker.
Okay. Probably, let me just recall what does this mean. This is just P I P J X X E D X equals 8 I J. And in this case, Pj is, in our case, this Pj is J's parameter polynomial. Let us continue. So the product of two determinant equals to the determinant of these two matrices. So it will be determinant of the sum of p k x I, p k x j, k from 0 to n minus 1, I j from 1 to n. And we should not forget these. These can be written in such a way. Here, for example, x1, 2, n over 4, and here the same thing. So we should multiply here the determinant of certain diagonal matrix, and then at the end of the day, this will be the determinant of I4 and we will write this as Kn xij. So by computation, we see that this probability is has such density. The determinant of a specific matrix. But of course, this does not, up to now, we do not see that in fact this is a determinantal point process because we have not calculated the nth correlation function. So, in fact, the nth correlation function, the kth correlation function can be calculated in the following way. And factorial to this probability. Let us write Pn x1 xn to dx1 dxn is Pn x1 xk plus 1 xn dxk plus 1 dxn. Then by some then the computation will be elementary, but in fact it's non-trivial. We can see, we will find that in fact this turns out to be the determinant of this. J. Okay. Okay. Any questions? Okay. Now let us turn to a general construction of determinantal point process. So there will be in literature there will be mainly two constructions. One construction is probabilistic. The other one that I would like to present is due to Russell lines, which I think is a very algebraic way. Before. Construction of determinantal point processes due to Russell lines. So let us now consider only finite discrete sets. E finite, of course discrete. We consider the countermeasure on this E, and we will identify these with the canonical basis of the L2 of E. The set we identify with the canonical, so here if it is E, the elements of the base E is E1 to En, then the basis of this is, we will use the same notation. Now we take a subspace of L2, and we consider the orthogonal projection which we will denote by Q. Of course, Q is just Q now is a E and E matrix. It's clear? So we will now fix any orthonormal basis of L. Any. Let us write D. D is the dimension L.
I'm sorry, how we would then, you take, okay, you enumerate your set in such a way that if E is represented by like the first 10 numbers, then you take the subspace in L2 of E generated by first M vectors of the basis, no?
So L2E is just functions on E, which is just functions on
okay,
E.
okay. Functions on E.
And you will, so a point in E correspond to the function which takes 1 at this point and 0 at all the other points.
Okay, okay, sorry, okay.
So we will define up to a multiplicative constant uniquely this thing. The exterior product of this will be an element in the exterior defined by the orthogonal sum of exterior product. That this is okay. So this probably is not a good notation. I will not write here. I don't know how many points in E. I will use here n. So a natural basis for this space so first of all, let us see what is if I have an orthonormal basis for a Hilbert space. What is the natural basis of the nth exterior product, tensor product of it? It's just we take so for here it's just we take the exterior product of distinguished n vectors chosen from the basis. And since we identify the basis by the set, so here it's in fact we have such notation sigma A, which is the exterior product of this for A, which is a subset. Of course, this is defined only up to some plus minus 1. But we can, for example, fix our ordering here, and we take this ordering here. So now, of course, since CL is an element in this space, we can expand it in such a way. We expand it with respect to these spaces, CL. Because CL, the modulus of CL equals to 1, it's a unit vector, we have 1 equals to this. Let us look at this this identity. 1 equals to the sum which is indexed by subsets of E. So this in fact gives a probability, because I can now define a probability such that the probability, the weight of a given subset A is exactly this quantity.
And it depends on the operator, yes, on the project.
Yes, so we would like to denote this by probability depend on L. Now, our claim is this as a determinantal point process. PL is a determinantal also we call determinantal probability sometimes. on the space of configuration. So the terminology is the following. If we say this is a determinantal point process, we say it's a determinantal point process on E. If we say it's a determinantal probability, we say it's a determinantal probability on the space of configuration on E. And our aim is to show this. But the construction, I think, should be clear.
But actually, the construction depends on the choice of a basis in L, no?
But in fact, this is artificial. We want to construct a probability on the space of configuration E.
Okay, understand.
So there's no.
But when you take scalar product, okay, you choose.
The scalar product is fixed. So
no, I understand. But you choose some. L is spanned by V1, Vd, yes. Okay, every L defines a point process. Yes.
L,
okay.
yes.
But nothing depends on the choice of, okay, how you choose sigma L, I mean, you take any V1, Vd, the base, yes.
Exactly. This does not change because L is d-dimensional. So the exterior D is one-dimensional.
Okay, I understand, but it is invariant under orthogonal transformation.
It's invariant because this is chosen in such a way it's also
okay. Okay, then it's invariant. Okay.
So let us recall the following fact. The inner product of two U1 UK and W1. Okay. This is the determinant of the square product, the inner product UI WJ or IJ less than K. This is the inner product for exterior tensor product. So here sorry I'm taking you so many time. V1 times exterior VD so this will be 0 if the A is not equals to D. Because the CL is a D degree exterior tensor product, so by the construction of the space, if they are of the different degree, they are orthogonal, so it has to be 0. And if the cardinality of A equals to CL, then we have what? V1, VD, and let us write E1 to ED when E1 to ED is the element of A. And you will see, we will see that this equals to V1 VD can project every E to the space L. Why this is true? Because we can always decompose each E by the parallel one and the perpendicular ones, and all those terms perpendicular one with the inner product will be 0. And since this is just a unit vector, and these two vectors are in the same one-dimensional vectors, this is in fact just the norm of this one. And this is one way to calculate it. So let us continue. We use this formula. So this is the determinant of Q, E, I, Q, E, J. But since Q is a projection, this will be Q, E, I, E, J. Here, ij from 1 to d, but we can in fact write it in such a way that this is QE F for EF inside A. Because here we make an assumption, we just denote A by this. And so, since A is a subset of the basis, this is the minor of the matrix Q restriction to A. So we have Q is a matrix, and the rows and the columns both are indexed by the points of E, and here we just take those. So for example, here, 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 this is A. Then we take this one, this one, this one, this one, and this one. This 3 times 3 matrix for in this picture. So at least now we know that the PL A is equal to the determinant of QA. This is in fact what we wanted.
Sorry, what is QA again?
Q is the matrix for the orthogonal projection of L.
Yeah.
A, so this is the minor, the submatrix indexed by the same column, column rows are indexed by A. To when can I?
No, you have 5 minutes.
Okay. So now, the main point is not this. We should now calculate the correlation function. But as we can remember that we have an intuitive way of defining the correlation function, which means the density of certain things. But in this discrete case, in fact, the correlation function will be even simpler. This is E1, certain E1 EK. It is just the probability, because underside is always 1, the probability of the events that this E1 to EK is included in our random configuration. This is by definition, this intuitive definition of the correlation function. And since we have this, so the probability is non-zero only when the subset has the same cardinality with the dimension of L. So this should be the sum. So let us write this as A. A is this site, this subset A. It's just the, okay, let us write it B. The probability of B union C, C is in the complement such that C plus, so the union equals the dimension, because otherwise it's non-zero. Now we claim that this quantity will equals to what? Will equals to the following thing. Now, in fact, you see we do not need ordering on the set because we have two things. The extra constant will always be cancelled. So this is uniquely defined. This is in the product. Before this thing is up to certain plus minus 1, minus 1. If we have this, but let us return to this claim later, a little later. Let us compute this. This is just the determinant of Q, E, F, E, F side B, and this is determinant. And in fact, we can, of course, what does this mean? This means, in fact, the Fe coefficient of the matrix Q. But by definition, this is exactly what we want. A determinantal point process is such that the correlation function is a determinant of a fixed kernel with coefficient which depends on this point. So we only need to show this claim. This allows me 3 to 4 extra minutes. Terminate. Let us calculate this quantity. This quantity.
I'm sorry, can you prove that? Let's take, I mean, if k less than b, you're going to consider k exterior power of b, of L, and then take the orthonormal basis and just consider the decomposition of B with respect to this orthogonal basis, and sum up all the probabilities that B equals to each term of this basis. This will be the same or not? Okay, take the case exterior power of L, and then sum up all the probabilities that B equals to the elements of this basis.
But it's not uniquely defined, so because to the case power, the L is d-dimensional, so the case power will be...
D choose K, and so on. I mean, B is a smaller subset of L.
Yes.
Okay.
Yes.
And then if you fix some orthonormal basis in L, then the probability that B equals to the element, some particular element of this orthonormal basis, is well defined as before.
But as I'm erased, the only case that the probability will be non-zero is in fact the set is exactly the same cardinality as the dimension of L.
Exactly. I mean, I mean, to reduce this computation to the previous one, we can fix fix the basis in L, and then we have D choose K.
Okay. You mean how to prove it?
Yeah.
But you see, in fact, it's just a little line, but
just not how to prove, just to understand that how it can be defined. Just this probability. I mean, this you just define this correlation function as this is the definition, yes?
This is definition.
Okay.
And after it's computation.
Okay.
And the main point is this claim. And this claim is in fact just properties of this exterior product. This will equals to, in fact, why this is true. You see that the inner product of this is the determinant of coefficient, which is just the inner product of the smaller, the simple vectors. And here it is just, we have here in fact QE1 to QE, for example. Okay, we will extend this to plus for the complement to certain thing. Here's ek plus 1, en, and this thing is the determinant of this part in the product. Here is Q, EI, EJ. And here, of course, there are orthogonals. Here's 0. Here is certain thing we do not know, but here it's 1. So this is we should be clear this identity. And then we can write it, we can decompose each E to be QE QE plus the orthogonal part. Here we keep the same. And now we move. This should be the sum of this C, which is inside this part, such that this C plus B is exactly equals this in fact here should be D, should be K in fact. K. Yes, this is D. Yeah. And QB union C. Plus no. We divide it in the same way. This in fact take some minutes to think about. But if you are interested, we can talk about this identity after the talk. Then this will give us in fact what is wrong. Sum in fact the sum of the same thing to similar things, and this will give us the same thing. Union C, K, E. And in fact, this will be the probability exactly because B union C is of the required cardinality, and this is in fact this. But I'm sorry, this part is too quick. But if you are interested, we can discuss later. Probably it's time for lunch.